Hi, this video is about collatz conjecture. I believe I have solved the conjecture. So, unless I'm wrong, which I could be, I really don't have a way to confirm the solution. I don't have skilled enough people around me who can confirm or debunk whether this solution is correct or not. So I'm posting it on YouTube so people would tell me. So if I'm wrong, just forgive my blunder because I didn't have anyone to tell me that I was wrong. So we will start with a brief explanation of what collatz conjecture is about. You can skip the explanation if you want. So collatz conjecture is you pick a number. If you have an odd number, you multiply it by 3 and add 1. If you have an even number, you divide it by 2. And collatz conjecture says that if you keep repeating this algorithm of multiplying by 3 and adding 1 to an odd number every time you come to an odd number and dividing by 2 every time you reach an even number, ultimately you will end up at 1 no matter what number you choose for all natural numbers. This is true. This is what collatz conjecture is. For example, you choose 5, you multiply it by 3, add 1, you get 16. Because 16 is even, you go to 8. 8 is even, you go to 4. 4 is even, 2, 1. Let's say 7. 7 is an odd number, you multiply it by 3, add 1, you get 22. Even, 11. 11 odd, 3 and plus 1, 34. Even, 17. 3 and plus 1, 52. 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. This is another example of how it works. And you can pick any number from 0 to natural numbers. For example, you 34, 52, 1, 1, 1, 1, 1, 1, 1, 1, whatever you choose, it's always going to end up a 1 if you do this procedure. That's what collatz conjecture is. So my solution starts with this. So we will wrongly assume that natural numbers is finite. 50% of natural numbers are even and 50% of natural numbers are odd. When you multiply a number by 3 and add 1, let's say you go to z, and z is 100% likely to be even, because whenever you multiply an odd number by 3 and add 1, it is an even number. So, and just like 50% number are even, 50% of numbers are odd in the set of natural numbers, if we assume it to be finite, wrongly assume it to be finite, every fourth number is divisible by 4, which means 25% numbers in natural numbers are divisible by 4. Or there's a 1/4 probability that a number you're going to choose in natural number is going to be divisible by 4. Same for 8. The 12.5% numbers are divisible by 8. There's a 1/8 probability that you're going to choose a number and it's going to be divisible by 8. Same for 16 is 6.25, for 32 is 3.125, and for 64 is 1.5625%. That's how many numbers there are divisible by 64 in set of natural numbers. So say n is odd. If n is odd, 3n plus 1 is 100% divisible by 2. And it has a 50% chance, because it has a 100% chance of being divisible by 2. It has a 50% chance of being divisible by 4. It has 25% chance of being divisible by 8. It has 12.5% chance of divisible by 16, and so on. And because this is true, presumably, if we go through this algorithm for every odd, and if we say in this algorithm that every odd number is step 1, if we say every time you multiply a number by 3 and add 1, and you call it step 1, and let's say step 1 is 3n plus 1, and then you go to an even number, and then you let's say you get an odd number after dividing by 2, and then you do it again, 3n plus 1, then you divide by 2, then you go 3n plus 1. That's 3 steps. And let us assume that number of steps are c, total number of steps are c. Every time you multiply a number by 3 and add 1, it is step 1, and there are c steps in total that solves the problem, or solves the, and or gets the number to 1 according to this algorithm. My theory is that c by 2, or the total number of steps in which you divided by in which you multiplied by 3 and add 1, in half of those steps, 50% of those steps, 50% of those odd numbers should be divisible by 4, approximately. 50% of the 25% of those numbers should be divisible by 8. Or c by 8, or 16, approximately 12.5% numbers should be divisible by 16. In other words, when you go 3n plus 1, you go even, then you go odd, then you go 3n plus 1, then you go even, then you go odd. Every time you go odd, you get an even number. That even number, whenever you 3n plus 1 a number and you get an even number, that number has 50% chance, or yes, 50% chance of being divisible by 4, 25% chance of being divisible by 8, 12.5% chance of being divisible by 16. That's my theory. And because this is true, if we assume, because we already have calculated for about 2 to the power 60 numbers for about, and we I'm not sure about this, but people say that 2 to the power 60 have been calculated, and they are known to end up at 1 according to collatz conjecture. So if this is true, then when you 3 multiplied by 3 and add 1, that 1 is negligible if you take a number above 3 to the power 60. So let us just assume that you are going to just multiply, whenever you do this algorithm, you are essentially multiplying the number by 3 and not adding 1, because 1 is negligible. So you are going through a procedure of multiplying by 3 and then multiplying by 3 and then multiplying by 3 c number of steps, or 3 to the power c. You are multiplying n by 3 to the power c. You keep multiplying, and then you divide it by 2 to the power c, because each time you multiply it by 3 and add 1, you also have to divide it by 2. So it's 2 to the power c, which means that every single time you get an even number, after 3n plus 1, you get an you divide it by 2, and the number of times you divide it by 2 is c. So you divide by 2 to the power c in total. And because I am assuming my theory to be correct, that 50% numbers are going to be divisible by 4, we are also going to divide by c by 2 and c by 4 and to the power c by 8 and so on, because divisible by 4 for divisible by 8, which is 25% numbers, and divisible by 16, which is 12.5% numbers, and so on. The total outcome ends up being 3 multiply n multiplied by 3 to the power c divided by 2 to the power c plus c by 2 plus c by 4 and so on, which ends up being 3 to the power c divided by 2 to the power c into 1 plus half plus 1 by 4, which is essentially a series equals to 2. So this ends up being 3 to the power c divided by 2 to the power 2c, which is 3 to the power c divided by 4 to the power c. When you multiply it by n, we know that the upper number numerator is smaller than the denominator. Therefore, after all these steps are done, for a number n, you should approximately reach 1. And why is that? Because 3 to the power c is much smaller. If c goes larger and 3 to the power c is much smaller than 4 to the power c, we have to choose a number that compensates so much that it approximately reaches 1. So let's take an example. Let's take 27. 27 is solved like this in about 35 steps, because you get 27, you multiply it by 3, add 1, whatever you get, you divide by 2 and you get 41. Same way you do 3n plus 1 on 41 and you divide by 4, you get 31. Same way you multiply it by 3, which is 93 plus 1, 94. 94 divided by 2 is 47. And this is the way it ends up being until 35th step, which is 5, where you divide by 16 and you get 1. So you are essentially this is the way I am taking steps to be. For an odd number, I say it's step 1 for every odd number, because I have to multiply it by 3 and add 1 to every single odd number. So for the first number, when you multiply it by 3 and add 1, you only have to divide by 2. Second number needs to be divided by 4 to get an odd number. Third number needs to be divided by 2 to get an odd number, and so on. So you can, what I found out is that there's like all numbers are divisible by 2, because it's obvious that after 3n plus 1 you get an even number, so every number is divisible by 2. This is total 35 steps, and the number of numbers divisible by 4 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 numbers are divisible by 4 in total. So we have total of 35 steps, and 17 numbers are divisible by 17 of them are divisible by 4, which is approximately 50%. As you can see, approximately 50, because it cannot be exactly 50% due to the problem of it getting below 1. It cannot go below 1. And the number divisible by 8 are 1, 2, 3, 4, 5, 6, 7. 7 numbers are divisible by 8, which is approximately 20% numbers are divisible by 8. 20% of these steps are divisible by 8. You have to divide by 8 in 20% of the steps, which is approximately equal, which is not exactly equal to 25%, the reason why I think it's not equal to 25% is because the number that I have taken, the number of steps is just too small for it to be exactly consistent. That's why it's 25%. It's not, that's why it's 20%, not 25%. It has to be approximately, because remember that we have to go to 1. Our issue is to go to 1. And let's take a different example where the approximation is more closely to be correct. For example, this is a random number that I chose. This is an odd number. So when you do this procedure, you have to divide by 4, then 8, then 8, then 4, 4, 4, as you can see. And every number is an odd number here in this list. Every number is an odd number. And I have multiplied by 3, added 1, and it divisible by 4. This one was divisible by 8, this one is divisible by 8. And I went on like this for like 78 steps. At 78th step, it goes to 1 after divisible by 16. So number of times it's divisible by 4, which in my calculation should be 50%, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. 39 numbers are of this sequence are divisible by 39 is divisible by 4, and 39 is exactly 50% of 78. 39 by 78 is 0.5. So exactly half of these numbers are divisible by 4. Approximately 23% numbers in this list are divisible by 8. When you count them, I counted all these 8s and I got across this result that 23% numbers are divisible by, which is approximately equal to 25%, more equal than the previous number. If we make a bigger list, it should go to approximately 25%. So, and remember, as the 2 to the power, as the power of 2 increases, the numbers which are divisible by that 2 to the power, that decreases. For example, it should be about 12.5%, but it's 9%, not 12.5%, which is approximately 4/5 of what it should be. Number divisible by 32 is 2.5%, which is not equal to 6.25%. But again, my insinuation is that it's because it needs a bigger list. As soon as we have a bigger list, this result should match. This result should be exactly, more closely approximation. There should be a more close approximation to this. So this is what I found out, and I think this is the solution to it, because when you multiply a number by 3 and you keep multiplying by 3 and you do it for all these steps, 3 to the power 78 for say, and because because all of these are divisible by 2 to the power 78, and all of these is divisible by 2 to the power 39, because 39 numbers are divisible by 4, and then divide by 2 to the power whatever it gets. The end result is that the denominator is larger than the numerator. Because the denominator is larger than denominator, this number is way smaller than 1, and when it's multiplied by n, which is approximately approximately equals it to 1, that n is going to take exactly c steps to be solved. For example, let's say 125 per 125, let's say c is equal to 125, let's say it took 125. So we have 3 to the power 125 divided by 4 to the power 125, which is equal to which is equal to about 2.413 into 10 to the power 16 minus 16. In other words, this number, in other words, because this is the end result, it has to be multiplied by 2.413 upon 10 to the power 16. It has to be multiplied by 10 to the power 16. In other words, 10 to the power 16, when it's calculated, when you make the collatz conjecture for any number that around about 10 to the power 16, it should approximately take 125 by 35 multiplied by 100. 725, which is approximately 357 steps. It should approximately take 357 steps to be solved, this 10 to the power 16 number. And again, this is what I believe to be, and I don't have a professional mathematician around me who can confirm if this is true. I'm just calculating it according to how much my brain allows it, and I'm coming up with this conclusion. Again, I might be wrong, I might be easily wrong. So this is, and the reason why we end up at 1, reason why every number ends up at 1, is because any number that you choose, 10 to the power 16, let's say, it is going to take c steps to be solved, where 3 to the power c, any number n is going to take 3 c steps to be solved, where 3 to the power c divided by 4 to the power c multiplied by n is approximately equal to 1. And that's why it's going to end up at 1, because it takes c steps. And because when you divide a number by 2, when you divide by 4 to the power this, it creates a downward trend. It goes upwards, but overall the trend is downward because the denominator is larger than the numerator. So that's my solution for the collatz conjecture. Please let me know if I'm wrong or I'm right, or if I made a blunder somewhere, because I cannot find a problem with what I found. Thanks.